scale is very different, and to me, I like the kind of bigger systems, things that I can see a lot better, and those I don't know, picofarads and nanoamps that happen for the gates on microelectronics. Again, that just wasn't really my style. But yeah, so the few things I'm going to talk about today, talk about how much is changing in our industry and power systems. As I'm sure you're aware and you've seen, there's a lot happening in the, energy industry. I'll talk about some new roles for electric vehicles. There's a lot of cool stuff that's going on there. Talk about kind of this renewable penetration into the, the bulk electric system or the grid, and a little bit about distributed energy resources or DERs. And then I'll talk a little bit about automation, control, and cybersecurity. That's something that I worked on for a couple years before moving into my current position in the Generation Interconnection group. So like we said, the power industry is old. We got some funny old pictures here from a long time ago, when in the 1800s, when the first power systems were here. And it's funny to see how much maybe has changed since then. And if people look at this and say, oh, there's things that have been around for so long, what's really exciting about working in this industry? And you might look at this, like this picture here is some even SDG&E stuff that's from the early 1900s. And yeah, I mean, you look at this, and is there really much difference in what you see here versus what you see, when you drive around today? And there really isn't. And we have a lot of stuff that's been in service for 50, 60 years. I worked on a project where we replaced this transformer. I have this big nameplate from it that was this transformer that had been in years so long that they had been marking on the transformer records from back in the 80s. And it does seem like that there is that idea this is like a dinosaur industry is not too inaccurate, but there's a lot more that's changing that's outside of the physical, right? What you see when you drive around is the lines and the substations and transformers, and the fundamentals of those things hasn't really changed. And you learn about some of that stuff in your 380 class, but really what's changing is the how much people need power nowadays, and how the availability is required 24/7. And people being out of power is just not really acceptable to the broader populace. And you might have heard, recently there was this big episode that happened in Texas, where there was a huge power outage, and millions of people lost power. And it has a lot of visibility, and this is where people are pushing for big changes in our industry, and for renewables and more integrated grids, and self-healing. And that's something that that's really where things are changing here in our industry. Is it's not the actual physical assets, right? Not your lines and your transformers. Those things aren't really changing, but kind of the brains that are behind all of that is really what's changing a lot. And who the players are, right? It used to be that you had these big centralized generation plants that were responsible for providing the power everywhere. Us, like a utility, we get that power from the generators and distribute it out to the distribution system and all the customers. But now people are starting, and solar really kind of opened the door for people to start producing their own power. And you have this people not only having enough solar for their homes, but then also are exporting that excess back to the grid, and that allows people to offset their energy costs and things like that. So there is a lot that's happening in the area of smart grids, and really in generation. And it used to be the idea of you being an independent power producer is very cost prohibitive. You would, if you wanted to build a big steam turbine like a show here on the right, I mean, there's no way that you at home are going to be able to do that, or even a normal sized business. But now with solar and battery storage, everybody can be part of the energy market. And that's something I'm going to talk about a lot, is the energy markets, and how you can sell power back to the grid, not only to offset your energy bills, but also to make money off of that. So So yeah, that's a big one. And then also just the penetration of resources, right? I mean, in the last years, there's been this huge uptake in residential. You can see that's the darker part of this graph here. The residential is huge on solar, non-residential being your commercial, and then the utility. That's like, what we do in power systems is study the impacts of those generators coming into our system. But it's no longer just your big central plant that does this. These are, a big accumulation of rooftop solar. Schools, I showed that picture up there. That's a big one we see a lot right now is schools, high schools, colleges, putting a bunch of solar in. Actually, at SDSU, there's a combined cycle plant. It's there down the street from the engineering building. If I don't know if you've been able to tour it or something, but that's a pretty cool plant that's over there. An older one, and I think it's natural gas or something like that. But um, the other one here is batteries. Batteries are becoming a big part of this. Not necessarily a generator, but because we have this, the solar is so much solar during the day the battery storage is really a good one to be able to offset that and produce power outside of the your normal times where solar would be available. This is a pretty busy slide, but basically it goes into talking about that this is really where the big change is again, that idea that the centralized plant is not the way we're structured anymore. Like on the left used to be that the market was just this generator is producing power for everyone through transmission and distribution. It goes to your customers. You have suppliers and people in the market that are participating with these large generators. Now we're looking at this more aggregated approach where you have a lot of small scale, PV, energy storage, microgrids that are all able to participate in the energy markets. And that's really the buying and selling of power. And there's different rules and regulations around that, but you can get a really good return on investment if you're putting these systems in and you're trying to offset your bills, and then you're also able to participate in the market. So there's a lot of really cool stuff that's going on here. Each one of these things takes a lot of study. That's what we do a lot of. We study these things for the impacts to the grid. Those things have changed so much. Instead of it being just one location where you had power coming along the transmission system almost radially, now you have to look at, okay, power is coming back from the distribution system onto the transmission system is causing issues. And there's a lot of research and things that are going on around this, but nobody really has the right answer of exactly how these things should be modeled and how they should be studied, and what really we should be looking at for them. And we have to take into consideration things like market uptake, like how many people are actually buying electric vehicles and how many people are installing rooftop solar, and it all has to do with how affluent the area is. And it's very cool because there's a lot of and not only just the design of the system, but there's all these other market conditions, and there's also the regulatory part of our business in which we work with the CPUC and others on the rules and regulations on how we're going to do stuff. So there's a lot that's changing in this industry, and a lot of it has to do with generation. But a lot of the smart grid part on communications and IP networks, and I'll talk about more about that in cybersecurity. But I'll pause there for a second. Is there any questions? Cool.
I just wanted to ask, how much emphasis is there into studying how to best store energy after it's produced?
Sure. And yeah, I mean the idea of the charging study, that's something we're looking into right now because there's this big uptake right now on utility scale batteries. So, what is the best way to store it? I mean, the best is to not charge during, and let me see if I have no, it's not here. So the best thing is to not charge during what is called the peak. Our peak happens at something like 6 to 8 p.m. and that has to do with people coming home and turning on their stoves and lights and air conditioning and stuff like that. So what we don't want is we don't want these big battery systems to be charging at that same time, because it makes the overall load increase. And if the load increases, then it means that our infrastructure, like our transmission lines and everything, have to be built bigger in order to accommodate for that, that coincident peak. Um, so the best time for the batteries to charge really is during the middle of the day, when the solar production is, basically overproducing. And let me see if I can't scroll through and find my good old duck curve. There it is. Okay, so in this case, this is what we look at, and we call this the duck curve, and it means that there's all this solar production, and this is like forecasting over a number of years. But this dip that's right here at the bottom, like the belly of the duck, is where we have all of this solar that is producing so much that there isn't enough demand for it. And this is the best time for batteries to charge, is during this time, or maybe in the what we call the super off peak, which is like the midnight to 6 a.m. time frame. But really, the one we really want to avoid is just them charging during this time, to where this isn't increased because of what that battery is going to look like is more load. Does that answer your question?
Yeah, it actually gives a pretty good insight as to what a designer would think about when designing a system like that. So thank you.
Yeah, yeah. And you do have a lot of hybrid resources now, where people are connecting more than just they're connecting, like they're applying with solar and storage, so that if they're overproducing, well, then they can charge it into their own batteries, and then during the nighttime, then they can discharge their batteries and be able to sell their power then, when the solar isn't available. So there is some cool stuff that's going on in that area. And I'm sure you've heard of like the home power packs and stuff like that, and second life batteries. So yeah, the battery storage is an interesting one. But again, the issue that it causes for us, or the concern it causes for us as a power system provider, is that if we don't manage that coincident peak, then really what ends up being is, by that battery being able to charge, it's going to drive upgrades across the entire system. That costs money for everybody. Like, you as a SDG&E ratepayer are going to have to pay for those upgrades, because of this generator. So that's really what we try to avoid, and we're really working a lot right now. But like I said, it's hard to study this stuff, because there hasn't been a clear way, since this is very new to our system, to have these huge battery systems. So yeah.
Well, if we're bringing up like kind of power that is being used up when you're charging a battery, is it more like reactive power or more real power? Because I know like if you have your laundry machine on, it's more reactive power that's being used in your house.
Okay. So you're talking about, like, the difference between an inductive and a capacitive load. So I think that, I'm not sure. I mean, there is a strict, or I mean, there is a prescribed power factor, and you're talking about leading and lagging power factors, for whether you have a resistive or an inductive or a capacitive load. I mean, these things have to maintain a certain range of power factor, which is like 0.95 leading or lagging. So it's almost all real power. So it's not like they're able to charge on, let's say, all reactive power, and then when they come back to discharge, they can do real power. No, their batteries are still charged by real power.
Okay. Well, that's cool. Thanks.
Yep, no problem. All right. The next one is EVs. This area is really cool. This is one of the rotations I got to do, and I really like this area. I keep up with this a lot in my, even in my own spare time, because I think the EV industry is super cool. And not only just that, EVs are starting to look cooler, and but that there's like these new roles that electric vehicles have. And for us in power systems, it's an opportunity, and it poses the same challenge that I just talked about with battery systems in general. One I wanted to explain first is, if you don't know about the kind of size, the relative size of some of these systems. So, when you go up to a DC fast charger, that's like, the one that takes 30 minutes to charge up your whole battery. Those things are the size, the demand of electricity those things have is the same size as like this big industrial, commercial building air conditioning unit. Versus like your level 2 charger that you have at your home is like, similar to running a dryer or something like that. But if you imagine, if you imagine, okay, I'm going to run my dryer for what, 6, 8 hours straight, or you're going to run this huge AC unit. Yeah, it's only 30 minutes or something like that. But again, we have to design our system to meet exactly what the max demand at that time is. It's not like, oh, over the period of it, it has to be at that moment. So, there's a lot of push for, oh yeah, let's get the EVs penetrated, let's get them out there, but we have to make sure that the system can handle all of these cars charging at the same time. But it does, like I said, it does present a different opportunity, and the big one is called vehicle to grid, and is basically the same, same thing I described about the battery systems, where the EV is actually pushing the power back onto the grid. And again, goes into this idea of, the market, and you can participate in the market potentially. I mean, what the use case we see is, okay, well, you take your car and you drive it to the office, and you're sitting there at the office the whole entire day. Well, what is your car doing at the time? Well, it's just sitting in the parking lot. Well, if you have it plugged into one of these, vehicle to grid type of charging units, well, you could be basically providing benefit to the grid while you're sitting there at your office. Now, you'd have to set up things like, okay, I need so much state of charge in order for me to be able to drive home. And, this is where there's a lot of variability in how this could actually work. But the technology is there, and we are doing pilots. We're doing pilots with buses right now. We've talked about this, and we have some other, things in the works on, testing out how this system would work. It causes a lot of interesting challenges. Again, that that where exactly is your vehicle going to be pushing power back onto the grid? Is it only at one spot? Is it at multiple places? A typical generator, it has something called a scheduling coordinator, and that person, you tell that person, okay, I'm going to have this resource available at this time, and you can dispatch it for whatever services, your whatever markets you're participating in. Well, in this case, well, you're gotta talking about your vehicle. Well, where is it going to be at? Is it going to be at your house? Is it going to be at your office, at the grocery store? So what's cool here, though, is that in addition to just the idea that, for us, this is the part we're looking at, right? Okay, you need to make sure that the grid is going to be able to handle it. But in addition to that, well, what does the communications look like between the vehicle and this charging unit? And how does this respond back to the grid? And what does the communications look like? And, how do you ensure that somebody isn't going to be able to hack into your car and, mess up with your car while you're just, trying to use your car to charge and discharge onto the grid? So there's a lot of really cool stuff that's happening in this area along vehicle to grid. And I think it's super fun, and there's these different. Oh, okay, I was forgot it. One of the things you can do with vehicles is, again, the market participation, and it has to do with frequency control, and it's called the regulation market. Is one of the ones that is one of these potentials for EVs to be able to participate in, and is basically just that when you have frequency, we have an AC system, everything has to stay at 60 hertz, so you can discharge and charge in order to keep that frequency where it's supposed to be. And that's one of the markets that you can participate in with electric vehicles. Um, the other one is this just vehicle grid integration, which basically just is not even the discharging part, but just charging. And again, goes back to that duck curve. And okay, well, when do we want vehicles to charge? Well, we'd like them to charge in the middle of the day, just like we talked about battery systems, or charge in the middle of the night, where anywhere that's going to be where you're not charging right when you get home. Because if you plug in when you get home, you're going to just increase that demand. And there's been a lot of research that's been done around, like the motivations for people to, not charge during the middle of the, at those peak times, by making the cost for charging a lot more. But it's something where, where do you actually do that? You maybe have to have control systems in place to do it. Those take, a certain amount of technology and things. And, what you have is people like IEEE and the SAE and UL that have all these standards that were made for generators, that now the vehicle industry, and that's where SAE comes in, are trying to figure out how they can create standards for the charging equipment and how the communications work. But IEEE sets out what is the requirement for that battery on the car to be putting power back on. And this is another one I'll talk about when we talk about renewable grids, is that you have to have a clean waveform, right? Your inverter has to be of a high enough quality to produce a good AC signal to not cause things like called harmonic distortion on the system. But they're the ones who, IEEE and others are the ones that set those standards. Well, now it's okay, well, the vehicle is going to have to meet those standards. So it means what, maybe a more expensive inverter on the vehicle, or maybe that means that the charging station has got an inverter. So these conversations happen, and between these big entities, but also at the the state level, people are arguing about where should the charger be at, and where the inverter should be at, and who's regulating it, and all this kind of stuff. So again, this is where there's just a lot more to the power systems than there used to be, and I think this is one of the cool areas. So I'll pause there again and see, is there any questions on EVs and kind of what's happening in that area?
I've got one for you, Sam.
Go for it.
So with these EVs, I'm sure for right now, it's probably pretty small scale. I may be wrong with that, so you can correct me. But I would guess that it's small scale right now as far as putting energy back on the grid, maybe even just testing. But in the future, do you see that, like, just from you talking about it, that seems perfect for like just like the public transportation, like the big buses, because those are going to go back to a depot at some time, and you could park them in the depot and just have them putting power back on the grid when they're done for the day.
Mm-hmm.
But do you see that expanding out to just like every person with an EV, they could park it in their garage, or is that like far-flung futurist kind of stuff?
No, I think if you ask someone like 5 years ago if it was far from future, they'd probably say, yeah, it is. But this is exactly what businesses like, there's a SDG or a San Diego based company called Nuve that's working on this. There are a lot of people that are looking into this, and there are bigger scale demonstrations of this done in, I think, in Europe. I want to say in the Netherlands. They have like an entire fleet of vans that participate in the market when they are not in use. And the way you talked about, and what we talked about, the school buses is like one of those perfect kind of use cases where how often does it get used? Well, twice a day is to take the kids to the school and then take them home, and otherwise they're just sitting there not doing anything. And then you think about how big a battery would need to be in order for a school bus, and that's a perfect thing to use for a market. And I think that's why we went after school buses as this kind of pilot. But I absolutely see this being something that is big for everyone, right? Could it be that you're using your vehicle? I mean, they have the thing called V2H, which is vehicle to home, which is, I mean, why couldn't you use your Tesla or your EV as your backup generator for home? Or that's where I think that's going to be a lot bigger. So yeah, I mean, right now, yeah, I think most of the demonstrations and things you're seeing would be on a smaller scale and kind of testing it out. But as we move forward in the future, the EV penetration becomes a lot higher. People are looking, because people are becoming more energy conscious and understanding that there's potential here. Then yeah, I'm sure, I mean, I would be down if I get paid, my car is making money for me when I'm sitting at work all day. That works for me. So
I
yeah.
think that works for me too. I'd be down with that.
Yeah. The interesting one though is, that how do you justify, what about things like depreciation? How many cycles can that battery go through before, it starts seeing degradation? And do you want your car to basically, lose value and depreciate more because you've been, using it to make money? And, what's the offset of that cost? And, there's a lot of different kind of human components to it. But I think when it does get figured out more, and that's one cool thing about working, I mean, at least for SDG&E, is that we're involved in a lot of these discussions at the state level, and to figuring out how we could do this and the benefits it has. And the entire nation is pushing for electric vehicle adoption, and this is just more benefits that EVs can have on top of just the emissions offset from from fossil fuels to batteries. So yeah.
Perfect. Thank you.
Yeah. Mm-hmm. Yeah, I think there was some commitment like 2035. I'm only speculating because I don't remember the exact date, but I thought I remember seeing something posted about that they had plans to electrify their entire federal fleet by some year, maybe like in the next 15 years or something like that. So yeah, and that's what we have to manage, though, right? If you imagine, I mean, the state has goals for 2030 of having, I think, 1.5 million EVs. And again, if we don't manage it and we don't figure out how to make sure that people are charging outside of that peak time, I mean, each vehicle that gets added is basically the same electric consumption as your entire house. Like if you take it over the entire year, your EV is like the same thing as your entire house. So every EV is like a brand new customer. And now, okay, if we add all these new customers, well, now we have all this new load and now we have all this new demand. And okay, now we're going to have to increase the size of, again, the size of our lines and all this infrastructure. And that means that everyone has to pay for that, right? Every ratepayer is paying for it. And that means that, okay, well, your people who are maybe not as, well off that are going to have to pay for other people to be able to charge their expensive EVs. So it's something that we have ratepayer advocates that are trying to make sure that these things are addressed, and we are too, because we see there's the impacts can be pretty negative on our system if we don't manage that. So yeah. Any others on EVs, or I'll move on? Cool. Yeah, so this is the big one that I do now. My group is responsible for studying impacts for these, all these big generators, big generators. I'm talking about, then thousands of megawatts. These are, ones that are, I mean, we only have a demand in our entire area in San Diego region of something around like 5,000 megawatts. And, you have big systems that come in. I mean, a lot of our imports come out from out in the desert area, but as I'm sure you all know, there's this huge push for, reducing CO2 emissions, and climate change is a huge issue that needs to be addressed. And, you mentioned Biden administration, they're, pushing for a whole lot of stuff. The chart is on the top right shows, where the greenhouse gas emissions come from the different sectors. And, two of those big ones are what we talked about, right? Electricity, that's what we're going to talk about now, is electricity production. The other one is transportation. So that's why, us as San Diego Gas and Electric and a lot of other, power companies, energy companies are focusing on these two sectors, because if we can, reduce the amount of emissions coming from electricity production and electrify a lot of transportation, we really, kind of address some of these largest producers of greenhouse gases. And you can see, on the left that, obviously things like coal, oil, natural gas have a lot more, CO2 equivalent for electric production than, the others do. And this just, goes to a lot of pressure. We get a lot of pressure from federal, from state. I mean, you have a lot of, at the federal level, you have all of these entities like, the Department of Energy, the EPA, the Federal Energy Regulatory Committee, and NERC. These are all entities that have, some say in how we operate, even us, like as we're a San Diego or a California-based company, but all of the rules that apply to the entire industry. And we're really stuck with working within the bounds that they set, and they're the ones that are, I mean, they are setting out regulations to ensure that we're looking at the grid at more than just our little area, right? It's great, cool, what if San Diego, we get to 100% renewables? That's great, but what's happening throughout the rest of the country, and making sure, because we have this enormous transmission system. Yeah, we have this enormous transmission system, and there's more to consider. And you can see that, I mean, I'll talk about the interconnections, but you can see this is an enormous transmission system, and you have to, because it crosses state lines everywhere, then it has to be regulated by the national level. And it is cool, because there's, that's where we kind of get in from engineering into kind of lawyering and doing compliance and stuff like that, because you have all these regulatory bodies that deal with the different sections. So, and the bottom left there is talks about the NERC interconnection. So that's actually like within this, in this picture, where the, it looks like this is basically a continuous connection. But this is the reality in the bottom left, is that we're divided into these interconnections where the entire Western region is all interconnected like our electric system is. And then the entire Eastern interconnection is all connected, within their transmission system. And then you got Texas down here, they like to do their own thing. Um, but but this is where you have to balance the power, right? Electricity, the production, generation has to meet demand all the time. So you have to balance how much is getting dispatched, and that goes into the market, right? You have the day ahead markets where they're saying how much power they think they're going to need. Then you as a generator are going to say, okay, this is how much power I can produce. And that's where this right section is about the RTOs, ISOs, and RTOs as regional transmission operators, ISOs as independent system operators. And that is, like where these are the big areas that are defined by FERC for those regions. And then down below is kind of how they end up looking, who the actual, what regions they actually control. But these are the people that if you are going to try to make money off of your generator, this is the market that you're going to go through. This is how you're going to end up being able to get into a market. And you can see that not everywhere in the US has a market, right? Like if you're in the southeastern US, you don't have an open market that you can get into in, the same way that we have here in California with the California ISO. I know another big one is PJM, which is kind of up in the, Pennsylvania and Virginia area. That's another big market. But this where it's cool, because depending on what region you are, it depends on how the rules and regulations and how you go through this process. And sometimes maybe it's not very engineering, but as engineers in this area, we have to give our input to our regulators and other people in order to make sure that the decisions they're making for how we're going to study the system, how we're going to process these things, who we're going to kind of let go through a faster process, or who needs to take a slower process, all that stuff gets, we give a lot of input to that. So I talked about the transmission. So these are some of the state regulators. We work with the California Public Utilities Commission a lot, Energy Commission, the California Air Resources Board, and then we talked about California ISO a little bit. But this is where you can. I mean, if I wanted to, I could really dive really deep into how we actually we create testimony. And you might go in front of the I was working with someone, we were in the EV area, that was, I don't know, on C-SPAN, because they were giving testimony on what the electric vehicle adoption is going to look like, and what the benefits are. And there's a lot of non-engineering stuff that you can do when you work in power systems. Again, a lot of it has to do with the regulation, but it does present some cool opportunities if that's what you're into. Again, talking about the renewable grids, I mean, the idea that renewable penetration is great, but we have to still make sure that it's going to work for our system and make sure that we can still maintain reliability. Everything used to be spinning generation. So when you see about, oh, well, the renewable grid is not going to work, well, that's not necessarily true. But there are specific challenges that come with that on inverter-based generation. And that's your solar and your battery storage. The other, your spinning generation, nobody is really building new generation. There's not value in it. There's the nobody wants to have a a coal fire natural gas power plant. But the reality is that's how we have historically maintained that 60 volts. And there's always been this kind of backbone of spinning generation that has been able to, it has what's called inertia because it is actually physically spinning. And when you have all these inverter based resources, well, you can lose a whole lot of resources all at once. And, how is the grid going to, see that? And, you have a lot of research that's going on. I mean, all I did was do a quick, Google Scholar search on power systems modeling, and everything is about, well, how are you going to model it and how do you study it? So these are the much more technical things that we also look at. And that's like in my group, I have one of our guys is a PhD, and the others have been working there for 12, 15 years. And the answer is still not clear on how exactly we study these things and how exactly are we going to be able to even model them, right? The models and the modeling software that we use looks at those big interconnections, right? A whole entire Western US. And, well, how is it that you're going to be able to study properly when you have a system that was made initially for this, again, centralized power plant distributed out to the customers? Now you got power flowing in all directions. So it definitely causes a lot of challenges, but, is another exciting area where there's a whole lot of research going on. And even us, we're doing what we can and trying to see, and we get some real time data for a lot of this stuff, and that's the kind of last part I'll talk about is that how we get that real time data to see some of this stuff, so where we can start without modeling having, I guess, real data to see what's actually going on in the system. So yeah, lots of exciting stuff going on with the big push for renewables, and a lot of pressure from national and state levels, but it's definitely cool, and we're making our way there. We got a lot of new generation coming on, and we probably will see those targets of 2030 and around there met for getting to a fully renewable grid. So yeah, any questions here?
I have another one for you. So, with the push for renewables and all of that, like, I'm sure that takes an entire, probably multiple teams of people working on the problems that need to be solved and things that need to be implemented. Is there an entirely different team that's working with the way things currently are? So those coal plants that you still have to deal with, because it's not like we're not in a vacuum here. Like this push for renewable energies, you still have the old non-renewable energies that exist, but they're also populations are growing, customer base is growing, all of that. So on your day-to-day, like how do you guys work together, or are you actually the same team? Like how do you interact?
Sure, yeah. So, I mean, you use the same software, really. I mean, it all really comes down to what are you using to actually study is software. And in the software, we basically take, a study case or a model that has everything in it, all the generation that's still in service, like you mentioned, I mean, we don't really have any coal in the San Diego area, but, if you were in, I don't know, another state or something, yeah, you would still be studying that. So the model, you'll still have all that in the same model. And honestly, some of the numbers that come from those generators establishes how we're able to, I don't know, how much generation we can trip at one time. And there's some other, nuances to what the biggest size old generator in your system looks like. But we are the same team. I mean, this is my team that I'm the team lead of right now, is we're looking at what is all the new generation that is requesting to interconnect, and that's over the next 10-year period. Basically, how much generation is going to come in? Is it going to be solar, wind, battery storage, maybe even natural gas? We don't have any of those, um, but we do have to look at them together. We can't really just turn, let's say, because you can, logically turn off the generator in your study model in order to then, let's say, dispatch all just solar or all, batteries, or have a mix of, all renewables. You can do that, but you still have to have those other ones in your system. So you're kind of looking at them at the same time, where at the same time we are working with, like I said, we have a couple PhDs that are working on things like this, on, what are the things that we might see, and we're involved in a lot of what called working groups, or stakeholder meetings where we work with, the NERC and FERC and DOE and the California Energy Commission. I mean, all these entities are all looking at this same issue, right? How are we going to address it? Well, you have academia, right? Like professors, like, I don't know, like Dr. Me or somebody else that might be in, that has, that's doing research in this area. And then you have us, who are the people who are like the owners of the transmission system, and we have to study those impacts. And it's cool because you might have like the one PhD we have. He used to be a professor, and now he's a engineer that works at our company. So we are it's a mix. I would say we do look at all of them together, and just kind of based on how you're dispatching, is what we call it, how you're dispatching the generation within your system, will differ based on the kind of study case you're trying to show. Does that answer your question?
Yes, it does. Yeah.
All right. All right, and the last is, how do we see all this stuff actually happen? And this is what I was working on for a couple years before is, automation, control, and cybersecurity, and what you have and what the picture here shows is a control center. So every transmission system has an operator that is looking at this stuff in real time. As I mentioned, you have to dispatch generation at the same time it's consumed. You have to maintain voltage levels, frequency has to be maintained. What happens when there's a power outage, or you're just doing something like maintenance. You need to take a line out of service in order to do work on it. So there has to be somebody there that is able to see in real time what's happening, and they need to be able to take control if they're or send out controls, what we call it, sending out controls to open a breaker that opens up a tie line, or close in something, or see that a customer is out of service. All that stuff has to come through a control center. And that visibility is really needed in order for us to maintain a reliable grid. And the other portion there is outside of a human only can act so quickly, but we have things that are like even like a breaker, your normal breaker at your house. If you accidentally, I don't know, put your uh, you know burn your toaster up or whatever, it's going to turn off the power to your house very quickly. Well, the same thing happens on the grid. It just happens at a bigger scale. And we have these, what we call the self-healing grid, and there's all these different devices that are out on the system that they'll automatically sense what's going on. They can turn it on, turn it off. Basically, okay, I'm going to trip. Okay, well, what if a branch falls across onto a line? Well, you want, it's going to burn up, and it's not going to be there anymore. But if you, in an old time, it would be, well, that thing turned off power, and now we're going to have to go and patrol the entire area, see what happened. We might not even see what happened if it was something like a bird or a branch or something that got caught in between the lines. Well, now you're talking about hours and hours and hours of people out of power, when you could just check and see if there's still an issue on the system. So we have things that are called reclosers that, when the power is off, it'll trip and then it'll close back in and see if there's still an issue. If there isn't an issue, then hey, cool. So you might see that sometimes. You might see like momentary outages where you go out of power for 5 seconds, maybe 45 seconds, and then bam, you're back in power, and you're like, oh, that was weird. Or maybe you never noticed because it was in the middle of the night. That's because we have these automated functions that will allow the system to heal itself. And that's a really cool area. There's a whole lot that goes into that. um, but with all that, with the control for your central operators and your automation, cybersecurity becomes a big concern. And there was this incident that happened in 2015 to the Ukraine power system, in which they were actually hacked, and about 250,000 people lost power because of this hack. And not that it wasn't known that there was potential for this to happen, but it kind of, I don't know, maybe made it seem a little bit more realistic. And there's a lot of work that we have to do around cybersecurity, and it gets regulated by those same entities that I talked about before. But this is a big issue, or not a big issue, but a big concern. And there's a lot of push, and I've seen posts and other things at the national level about Biden administration pushing for cybersecurity enhancements across the entire grid, because I mean, we see it, right? Any company now, it seems like, is vulnerable to be getting hacked. And with us doing all these things in having better visibility, having better automation, having all allowing different people to get into the system and becoming part of the generation and these smart grids, a lot of that has to come with IP networks, because that's really the only way you can manage that much data and manage that much control and everything. So with any time you introduce an IP network, you have vulnerabilities. And that's a big one that we fight with, and that I did a lot of work on in our group. We have a lot of compliance we have to do about this, and doing active scans and learning about IP addresses and MPLS networks and things that me, as going into power systems, I thought I wasn't going to have anything to do with. I end up giving testimony and designing systems, and implementing authentication and encryption. So this just, again, just goes to show that there's a whole lot that's, going on in our industry, in the power systems. There's so much more than just, the old lines and transformers and breakers. There's a lot going on, and if you're interested in the area, there's a whole lot that's happening and a whole lot of companies. SDG&E is one of those, but we're definitely not the only ones. There's a lot in San Diego. There's a lot throughout the entire country. So if you're interested in power, it's a really exciting time to be in the power industry and energy at all in general. So, I know that it seems old, and there is definitely some truth to that, but there's a whole lot of exciting stuff that's going on in our industry. So that's really all I had. Is there any more questions or anything?
I had a question.
Sure.
So I guess this summer, I'm going to be interning for the Tesla microgrids team, and
Cool.
so curious of like what kind of things I should be expecting in terms of like I know that they aim to integrate a lot more microgrid systems across the like the West Coast.
Sure.
But then in terms of like trying to integrate and implement these microgrid like systems, these mega packs, do you think in like your own opinion that it's something that's feasible as an option to replace power generation throughout like the Central America kind of power area? Because it seems really like when I think of like Tesla's supercharger network, it's very well and very easily built up around like this California area, this entire like
Mhm.
West Coast, and then the East Coast. But then when it comes to
Yeah.
like this like the Midwest part, it becomes
Mhm.
a bigger challenge. Do you see like possibilities in this infrastructure becoming more widespread throughout the actual central part of the U.S. in the future?
Yeah, I know that's a really cool opportunity to do that. I mean, yeah, I mean, we have a microgrid that's out in Borrego Springs. I mean, I don't know if you know where Borrego Springs is, but it's basically out in the desert, like hours east of San Diego. And the reason is because of that, right? You don't have this big integrated network where there's like exactly what you're talking about is that a huge Tesla supercharger station that's out in the middle of, Arizona or West Texas or something like that. Well, where's the infrastructure in order to allow that much charging? Well, yeah, then the microgrid makes absolute sense. You have solar or wind or whatever it is that's your generation being produced, and then you can store it in batteries there until you have a vehicle that comes and charges, and then you can charge it up, and yeah, you're just kind of cycling through. And that's the intention of the microgrid is to, not need that grid connection. I mean, we look at microgrids more like in a, okay, if you lose the grid in this area, how can you, basically still give people power, just kind of like a backup generator. But the use case you're talking about, yeah, absolutely feasible. I mean, it'll just be, I'm not sure exactly what you'll be doing, but there's a lot there, the communications, how much is it charging, level of charging, how much is it the solar can produce, what if it's, everyone comes and charges at night and then somebody's coming in the morning, how are they going to get power? So, figuring out what size of systems. I mean, yeah, it sounds like I don't see any reason why it isn't feasible. I mean, the technology exists. The only ones you got to run into is things like permitting, right? You still have to get your local jurisdiction to allow you to build it. And honestly, there's places in the US and different states that are, absolutely not okay with a solar generation. And I don't know, there's different sentiments in different places in the country, but yeah, I mean, it's absolutely technically feasible. Yeah, definitely.
Thank you.
Can you talk more about the rotational side of SDG&E? Like,
Sure,
is that
sure.
hopping around to different programs and that
Yeah.
they have?
hmm Yeah, sure. So we have for the engineers, and actually there are like I'm trying to think of, there's a couple different. I mean, basically, if you come into SDG&E in the, as an entry level position, we usually have a rotation program. So how it works is, you would go through, the interview process. If you get, brought on board, then you get basically assigned to your first rotation. So my first rotation was in the protection and control area, and you're there for 6